Welcome to AP Environmental Science. In this video, we are going to discuss nuclear energy generation. We're going to do a brief overview of radioactivity and half-life. We'll talk a little bit about the process of nuclear fission and how that fission can be captured and harnessed to generate electricity. We'll also briefly discuss the pros and the cons of using nuclear power as a source of energy, along with the three major nuclear accidents. Recall that atoms are made of protons, neutrons, and electrons, and if you have an atom with a different number of neutrons, we call that an isotope. And isotopes, if they are unstable, can go through this process called radioactive decay. Now, radioactive decay is the spontaneous splitting or breaking apart of an unstable nuclei, and this can release alpha and beta particles, or alpha, beta, or gamma radiation. Now, alpha emissions have two protons, two neutrons, and really all you need to know about this is alpha emissions are nothing to really worry about, and they can just be stopped by a single sheet of paper. Beta emissions are a little bit more dangerous. These contain 1 electrons, and they take a little bit more of a protective level, which would be a single layer of metal. But gamma radiation, this is what we really need to worry about. Gamma radiation contains high energy electromagnetic radiation, or photons, and gamma emissions or gamma radiation can only be stopped by a thick layer of lead that's generally 5 centimeters or thicker. Now, if we're looking at the half-life of radioactive material, or the amount of time it takes for half of that radiation to decay away, or half of an atomic nucleus to decay down to its reaction products, we can use this half-life graph. Now, on this graph, we start with 100% of the material, and after one single half-life, we're down to 50% of that material. After the second half-life, we're down to 25%, and we keep cutting that remaining amount in half as we go through each individual half-life. Now again, as we go through this radioactive decay, the original atom is decaying or splitting into something different, or another atom, and in that process we're releasing that radiation. Now in general, after an item has gone through 10 half-lives, we consider that to be radioactively safe. So let's look at an example here. If we look at cesium-137, this has a half-life of 30 years. And if you have a question that asks how long will it take until radioactive safety is reached for cesium-137, given a half-life of 30 years, you can set it up using the following equation. So you can say 30 years per half-life times the 10 half-lives until we reach radioactive safety, make sure the units cancel out, and you end up with years as your unit, and it will actually take 300 years to reach radioactive safety for a set amount of cesium-137. Now, when we're thinking about nuclear power, we are using this radioactive decay in the form of nuclear fission to generate heat. And what happens here is a chemical chain reaction where our starting material of uranium-235 is broken down or split into what are called fission products. Now, as the uranium-235 is broken down, it releases heat energy, it releases these two fission products, or the two main chunks of the original nucleus, and it releases more neutrons. And those neutrons go on to strike other uranium-235 atoms and proceeds to split them in half, again releasing more heat energy. Now, if we're looking at a nuclear power plant, our goal here is to generate heat, to create steam, to turn a turbine, to generate electricity, just like our goal at any other type of power plant. So in your notes, you may want to draw a brief schematic of what's happening in a generalized nuclear power plant. Keep in mind, you'll notice there's separate loops going on here. And that's because we're trying to prevent any of that stuff that's in that reactor core from coming in contact with that next loop, or coming in contact with the outer loop, or coming in contact with the environment. So what happens here is inside of the reactor, we have these uranium pellets that are stored in these long columns called fuel rods, and this is where that fission is taking place. And that creates heat. And this heat is then transferred through tubes to a chamber that's full of water that then is used to generate steam. And that steam then goes on to a turbine to then spin that turbine to spin a generator to make electricity. And that steam is then cooled in a condenser. And that condenser is what has an additional loop here going out to a cooling tower that then helps to recycle this entire process. Now inside of that nuclear core, or that reactor core, that's where we have our fuel rods, but we also have these things called control rods. And those control rods typically have a substance such as boron that helps to absorb these neutrons to control or slow down the rate of nuclear fission. Because of course we do not want that to get too hot inside of the core and then melt down our fuel and create a puddle of fuel at the bottom of the reactor core. That's what a nuclear meltdown is a puddle of fuel at the bottom instead of being in these nice columns. Now, that radioactivity that's used in these fuel rods remains radioactive for a long period of time, even after it's no longer efficiently creating heat. So the waste from a nuclear reactor remains radioactive for up to 24,000 years. That's the 10 half-life safety mark, is 24,000 years. Really long time, much longer than any of our lifespans. So what do we do with that? Well, the spent nuclear fuel is initially stored in these pools on site at the nuclear power plant, and after a set amount of time, it then gets transferred into these dry cask storage. So a dry cask is this big column or big cylinder here that is just filled with these spent fuel canisters. It's reinforced with concrete and steel. They're very sturdy, very stable, and they are just stacked up next to each other on site. Now again, in order to create a certain amount of energy from nuclear fuel, it takes much less initial fuel than that same amount of energy from something such as coal. So we consider this a pretty small or minimal amount of waste. But then what were we planning on doing with all this waste? Right now it's stored at many sites across the country. In the United States, we had planned on using Yucca Mountain as a centralized nuclear repository. And Yucca Mountain is completely built, it's ready to go. However, right before it opened to start accepting waste, then people put the brakes on the project and decided, maybe we should just keep doing what we're doing right now, and we didn't want to have this nuclear waste stored in my backyard, so to speak. And that's what NIMBY means, not in my backyard. People who live in the area kind of put up a little bit of a stink where it's like, hey, maybe we shouldn't be bringing this here, so that project was put on hold. So again, as a result, we have nuclear waste stored at many sites throughout the country. If we look at the map here on this side, each dot or triangle is a location where nuclear waste is currently stored. So it's all over the country. And that nuclear waste can be categorized based on the level of radioactivity. Again, these dots are showing where high-level waste is stored, not necessarily the low-level waste. Low-level waste is things like clothing, tools, paper, generally not dangerous to handle. Intermediate waste requires a little bit of shielding, but again, not a huge deal to have to deal with. It's usually stored in a warehouse. The high-level waste, that's what we're concerned about, and that contains those spent fuel rods. Briefly, I want to discuss the pros and cons of nuclear. The pros, it does not produce any methane or carbon dioxide emissions in the process of generating electricity. It has a relatively high energy output and a pretty low cost of day-to-day operations. Additionally, nuclear energy does not require the mining of fossil fuels and all of the environmental impacts that are associated with it. And again, because we're not releasing methane or carbon dioxide or really any air pollutants, we're not seeing any of those primary or secondary air pollutants. We're not seeing any acid rain associated with this. Overall, it's a pretty consistent and good thing. There are some drawbacks to using nuclear energy as our power source. Even though nuclear energy produces a small amount of waste products, those few waste products remain radioactive for a long period of time, so that creates this long-lived hazardous waste. Additionally, nuclear accidents are extremely rare, but when they do happen, they are extremely devastating and can destroy and disrupt the environment for a long period of time. Nuclear energy, along with all other fossil fuel energy sources, has the potential to create thermal pollution in that cooling process. Nuclear energy is very expensive to build initially, however, it is very cheap to continue producing after you've built the facilities. It does require a little bit of mining for those initial supplies to build the nuclear power plant and to extract that initial amount of uranium. However, and we did not discuss this in this video, that uranium fuel that's used can be reprocessed and used again, but that reprocessing does have its own suite of benefits and drawbacks. And overall, because you are using something that you are extracting out of the ground, and there's only so much uranium in the Earth's crust, that makes nuclear considered a non-renewable resource. Now I want to briefly discuss the three major nuclear power accidents. They happened at 3 Mile Island in Pennsylvania, they happened in Chernobyl in the Ukraine, it was the USSR at the time, and it also happened in Fukushima, Japan. Now, you do not need to know the great details about what happened at these accidents, just know kind of where they are, when they happened, and a general idea of the impact on the environment. So the first accident happened at 3 Mile Island in USA. Now, this accident did not release any radiation into the environment, it did not have any explosion, and this did not cause any long-term damage. What happened here is a water pump that helps with the cooling system failed and partial meltdown occurred in that fuel. Again, the operators were able to observe this really quickly, they shut things down very quickly, and there was no major accident that happened here. So this is pretty negligible. It's kind of a bit of a stretch to call this an accident. It was just more of a whoops, something went wrong, but we fixed it right away. The actual real major issue here happened in Chernobyl in the Ukraine in the former USSR. What happened here is a improperly conducted safety test resulted in an explosion and a huge release of radiation. So what happened in this safety test is they were trying to test to make sure that if you shut down power to the reactor, the residual amount of power from the turbine slowly spinning down would be enough to power those, to kind of hold things over until the backup generators got back online. But what happened here is the test happened, they checked all the boxes, they're like, okay, we got it good. And then when they went to get everything back up and running again after the test, when they inserted the control rods back into the reactor, they didn't realize that the control rods were designed such that the tips of them had graphite, and that graphite initially sped up the reaction. And that quick little bump up before the control rods were fully inserted caused the reaction to go exponential. It started to melt down the fuel core, and that's what led to the hydrogen explosion. The third nuclear accident happened in Fukushima, Japan, and this was actually caused by a natural disaster. This also emitted some radiation into the environment. So what happened is there was an earthquake just off of the coast of Japan. That earthquake was measured at the power plant, and it triggered the emergency shutdown. Shortly after the earthquake, there was a tsunami, so that large wave, that came and hit the shoreline. And that tsunami actually flooded the reactors, knocked out the power supply, knocked out the cooling system, and that caused 3 of the 6 nuclear reactors there to start to melt down. Again, this accident was actually deemed preventable if there would have been better reinforcements of the seawall and of the buildings themselves, and if the reactors were designed a little bit differently, the entire accident could have been prevented. Now, in summary, you should be able to describe radioactivity, half-life, and the process of nuclear fission, along with how that fission can be harnessed and used to generate electricity. Additionally, you should be able to describe the pros and the cons of using nuclear power to generate electricity, and you should be able to describe the 3 major nuclear accidents. Please send me your questions here at the end, and I hope that as you watch this video, you were able to learn something.